let us take a look at the second method of determining the points where the root locus branches may intersect the j omega axis or the imaginary axis. In the first method, essentially what we are doing is we are trying to find out if the characteristic polynomial had a root which was purely imaginary, and of course we know that if j omega is a root, then minus j omega is also a root. And so to determine such an omega, you just replace s by j omega and equate the characteristic polynomial to 0, split it into its real and imaginary parts and equate them separately to 0, and you get two equations in two unknowns. One of the unknowns is of course the gain Ka, for which there will be an intersection, and the other is the value of omega corresponding to the point of intersection. Now there are ways of solving these two equations. For example, by eliminating k, the gain Ka, you will get a polynomial in omega, and then you have to find out if it has any real roots. The second method is a little different. It makes use of the angle or argument idea, that is the angle condition or the argument condition, and it is useful only if you are willing to use a calculator and make a number of trial calculations. As an analytical method, it is not a good one, as we will see. So what is the problem? I want to determine whether there is a point j omega which is on the root locus. Now what does the angle condition tell you? The angle condition tells you that a point in the complex plane is on the root locus if and only if what happens? If and only if the sum of all the angles subtended at the zeros minus the sum of all the angles subtended at the poles, this difference is equal to pi radians or 180 degrees alternatively, plus or minus a multiple of 2 pi radians or a multiple of 360 degrees. That was the angle condition. So to find out whether a point on the imaginary axis, which looks like this j omega, whether it is on the root locus, we will have to find out the angle subtended by this point at the various zeros and at the various poles, and then write down that expression sigma angle subtended at the zeros minus sigma angle subtended at the poles equal to pi plus or minus 2k pi. Now if I choose a particular value for omega, for example I choose, let us say j2 instead of any arbitrary unknown omega, if I choose a point, let us say j2, then it is not very difficult to find out if the angle condition holds. In fact, if you remember earlier, I had asked you to find out whether the point 2 plus j2 was on the root locus by using the angle condition. So here for example, we want to check whether the point j2 is on the root locus, or in other words, there is an intersection of the root locus branches with the j omega axis at least one point, namely j2. Now of course we will not be lucky that this j2 will be on the root locus, and therefore I will have to repeat it for another point, let us say j1 or j3, and really there is no end to it, because I may try 10 different points, I may find that none of them lies on the root locus. Still there may be a point which does lie on the root locus. But by making these computations, one can get some idea as to whether there is likely to be a point which lies on the root locus. How do the computations go? They go as follows. I first sum all the angles made at the zeros. So here is this point j2, here is the 0 at 2. So I draw this vector going from the 0 to this point, and I have to calculate the angle here. Now incidentally, when Evans introduced this method, he did not have the pocket calculator available. This was in the 1950s. The pocket calculator had not been invented. Engineers of that time, and even I continued to use this tool which is known as the slide rule. Today probably you will not even see one. So multiplications and divisions were carried out, and even trigonometric ratios were found out, and logarithm and exponential with the help of what is called the slide rule. So slide rule will enable you to add, enable you to multiply, divide, but not to add or subtract. The slide rule was used for multiplication, division, raising to a power even, and exponential trigonometric calculations. But here I need to know the angle, and so what Evans did was he combined slide rule with a device which we use for measuring an angle. And what is that device? That's a protractor. With the help of a protractor we can measure angles, and so Evans combined these two into a new instrument which he called a spirule. And after this was invented, engineers found it quite useful, and so it was being used for quite some time. I bought a spirule for myself and learned how to use it. Today, of course, you neither have the spirule nor do you have the slide rule. Fortunately, you still have the protractor, so you can measure the angles if you want it. But today you have the pocket calculator, so you can calculate the angles more quickly. So for example, what will be this angle? I don't want to measure it. How do I calculate it? Now you can see that to determine an angle, you need to know two sides of a right angle triangle. Then you can find out using the inverse trigonometric function the angle. Now what do I know in this case of this right angle triangle? I know the vertical side and I know the horizontal side. In other words, I know the two sides which enclose the right angle, and therefore if I call this angle theta, then I can immediately find out what tan theta is. Tan theta will be this height, which is 2, divided by this base, which is 2. So tan theta is 1, and fortunately I don't have to use a pocket calculator to find out what is the angle whose tangent is 1, and the angle is 45 degrees if you want an acute angle. So this theta is 45 degrees. So what is this angle? Angle subtended at the point by the 0, measured in the anticlockwise or counterclockwise direction from the positive real axis. Here is the positive real axis, here is this vector pointing towards J2 point, and so I have to measure this angle in the counterclockwise direction. So what will this angle be? It will be 180 degrees minus 45 degrees, or in other words it will be 135 degrees. Now if this was not 2 but this was something else, then I can do it on the pocket calculator by simply entering this number first, dividing it by this number, and then using the appropriate mode on the calculator to get tan inverse. So just 2-3 presses of the calculator, enter the height, then divide command, enter the base, and then tan inverse. For that you may have to use the inverse mode and then press the tangent key, and you will get the angle, but you will get this angle theta. The calculator does not give you all possible angles. For example, the calculator will give you 45 degrees but will not give you 225 degrees, which is also a correct answer, because as we know, the tangent and the sine and the cosine repeat their values not only after 2 pi but even for earlier increments or differences. So the angle here is 135, and when using the calculator you should have the figure in mind so that you get the correct angle. Now what about the angle subtended at the other 0, which is this one? Now that is easy. This is 2 divided by 2 is 1, tan inverse of that is 45 degrees, and it is this angle, so this is 45 degrees. So what is the sum of the angles subtended at the zeros? There is 135 degrees here, there is 45 degrees here, so the total is 180 degrees. So sum of the angles subtended at the zeros is 180 degrees. Now we have to calculate the angles subtended at the poles, and there are 3 of them. Now this is where you will have to use the calculator actually, and you cannot use any ordinary knowledge of trigonometry. For example, now take this pole at -1. So what is the angle subtended? It is tan inverse of height is 2 divided by 1, or tan inverse of 2. Now you will have to look it up on your pocket calculator. Do it. Roughly speaking, from the figure it looks like it is an angle greater than 45 degrees, it is an angle less than 60 degrees. Let's say it looks somewhat like an angle of 65 degrees. But you check it on your calculator what tan inverse of 2 is. Alright. Then I have the second pole which is at -3. Here is the vector going from this pole to this point J2. Now what is the corresponding angle here? The height is 2 and the base is 3. So it will be tan inverse of 2 by 3. Now what is tan inverse of 2 by 3? Well, once again you will have to use your calculator, but let me say for the moment that it is something like 25 degrees. There is one more angle to be calculated from this pole to the same point. So 2 divided by 4, so tan inverse 2 divided by 4, find it on your calculator, it is tan inverse of 1/2. So it is actually the complement of the tan inverse of 2, and so it is going to be 25 degrees, as a result of which this middle angle will not be 25, but it will be something else, let us say 28 degrees. Alright. So we have 3 angles now, 3 angles subtended at the poles. You should be making exact calculations. Now what is their sum? Their sum is 65 plus 25, because tan inverse 2 plus tan inverse 1 by 2 is 90 degrees. 90 degrees plus 28 degrees is about 180 degrees. This minus this is not close to 180 degrees at all. So this point is not going to be on the root locus. The point J2 will not be on the root locus because it does not satisfy the angle condition. Now this was just one sample calculation. I can do another calculation very quickly. In fact, we have done that already when looking at the real axis portion rule. What about the point 0, the origin? Is it on the root locus? Find out if the angle condition is satisfied. So what are the angles? The angle made here by 2 is 180 degrees, and the angles made by all the other things on the left hand side is 0 degrees, and therefore what is the conclusion? The conclusion is that sigma angle at zeros is 180 degrees minus sigma angle at the poles is 0 degrees, and therefore the difference is 180 degrees. So the point 0 or the origin is on the root locus. And of course we had found that out earlier by using the real axis rule. Why? Because if you consider this segment of the real axis, then for any point on this segment, the number of poles and zeros to the right is odd, in fact only 1, and therefore that point is on the root locus. So we have found out one intersection with the j omega axis, but there may be more. What is the value of Ka for this? The value of Ka can be calculated, and what was the rule? Remember the rule? Ka was the product of distances to poles divided by distances to zeros. So for this point, the origin, the value of Ka will be given by distances to poles minus distances to zeros, and that can be found out. In this case again, it can be found out by calculation. If you have to use your calculator, then again there are simple calculations to be done. If you use a scale, then you can measure the lengths also. For example, there are the 3 poles here, this one and this one, and what are the 3 distances? So this is the hypotenuse of the right angle triangle. This is one side is 2, the base is 1, and so the hypotenuse squared is 2 squared plus 1 square. So do that, take the square root of that on your calculator. I will not do it using a calculator right now. I will write down the exact expression for it. It will be root 5. What about the distance to this pole? 2 this way, 3 this way. So 2 square plus 3 square, that is 13. Square root of that is root 13. That's the length. So root 5 plus root 13. Third one is 2 here, 4 here. So 4 plus 4 square is 16, 20. So plus square root of 20. Distances to the poles divided by the distances to the zeros. There are only 2 zeros here. This one, so this distance is 2 square plus 2 square, that is 8 divided by the square root of that. Therefore square root of 8 plus this is the second 0. So 2 square plus 2 square is again 8, square root of that plus square root of 8. So I get this Ka equal to this number. Remember, Ka is the sum, no, not sum, I made a mistake. The sum occurs in the case of angle condition. In the case of the formula for the gain, what occurs is product and ratio. For the angle condition, sum of angles minus sum of angles. For gain value, product of distances to poles divided by distances to zeros. So square root of 5 into square root of 13 into square root of 20 divided by square root of 8 into square root of 8, whatever that number is, that is the value of the gain k, for which there will be a root at the origin. But if you want to find out if there are any other intersections, then I will have to repeat the calculations that I did for this point J2 by looking at the point J1 perhaps and J3 and so on. Of course, what happens is that when I make the calculation for J2, we found out that the angle was 180 degrees. At origin, the angle was 180 degrees, 180. For J2, the angle was about 118 degrees. We can take another point, and we can take the point which is sometimes said to be the point at infinity along the j omega axis. In other words, it is a point j omega where omega is very large. Of course, how large is very large? Well, that depends on the calculation you are making. So, suppose you have a point which is here j omega is very large compared with the poles and 0 distances. So, here is my pole which is 0, which is 2, here are the poles -1, 0, -2, poles -3, another pole -4. Now, let us make the angle estimation again. Remember, I am saying that j omega is such that omega I am going to consider very large. In fact, so large that I will not be able to draw it on my paper. So, I have to imagine that it is way up here somewhere. Now, what about the angle subtended by that point at 2? Now, it does not require much thinking to conclude that it will be an angle which will exceed 90 degrees, but by a small amount. So, it is going to be 90 degrees plus a small amount. How small will depend on where the point is. If I take omega equal to 10,000, the angle will have some value. If I take omega equal to 1 million, the angle will be still smaller. So, it will get closer and closer to 90 degrees as I increase omega, but it will be always a little greater than 90 degrees. What about the other angle at the other 0? It is this one. By a similar argument, it is also going to be very close to 90 degrees, but it is going to be less than 90 degrees by a small amount. And so, the total contribution of the two zeros will be almost 180 degrees plus or minus a small amount. Larger the value of omega, smaller the amount. All right. Now, what about the contributions of the 3 poles? By a similar argument, each of the poles will contribute 90 degrees plus a small amount. So, the 3 poles together will contribute 270 degrees plus or minus a small amount. So, sum of angles at the poles will approach zeros, will approach 180 degrees. Sum of angles at the poles will approach 270 degrees. So, this difference will approach, and therefore, I am writing will be very nearly equal to minus 90 degrees, or alternately I can write it as 270 degrees, close to it, nowhere near 180 degrees. So, in other words, there will not be any intersection with the j omega axis for a sufficiently large value of omega. This is a conclusion I can draw by looking at the angle condition and considering the limit as omega tends to infinity or as omega becomes very large. For the origin, the calculation was very simple, and we found that the origin was a point on the root locus. The problem is there any other point on the root locus on the j omega axis? Unfortunately, in this method, I cannot do anything else but to keep trying, and then maybe I can interpolate between 2 points. For example, going back here, if the angle for this one is 118 degrees, the angle here is 180 degrees, most probably the angle for any point omega here may be between 180 degrees and 180 degrees, 118 and 180 degrees. It may be, there is no assurance. Now, there is a way of using this method which is harder, namely to write down the angle condition for a general point j omega, and I will write it and you will see how difficult it is going to be. So, if I have a general point j omega, now I am going to write down expressions for the angles, and you check that they are correct. So, the angles made at the 2 zeros, one of the angles will be tan inverse of omega divided by 2, but not quite that because of the location of that angle. So, it is pi radians minus tan inverse of omega by 2 plus the other angle is tan inverse of omega by 2. This is the other angle subtended at the other 0, and so you will notice that in this case these two angles add up to pi. That's a coincidence because the two zeros, one of them was at +2, the other was at -2. So the sum of the two angles just adds up to two right angles or pi radians. So omega drops out here, but that's my luck. In general, it's not going to be like that. Now minus, there are three angles, and what are they? They are tan inverse of omega divided by 1 minus tan inverse of omega divided by 3 minus tan inverse of omega divided by 4. This whole thing should be equal to pi radians or 3 pi radians or minus pi radians and so on. So I have an equation for omega. Unfortunately, it's not a simple equation, it involves the tan inverse function. So how do I solve it? One way, as I told you, is just to substitute various values of omega and see whether you get close to a root or a solution. The other alternative is to take the tangent of both the sides of this equation. When you do that, and then you have to use certain trigonometric formulae. For example, you will have to use the formula for tan of theta 1 plus theta 2, tangent of theta 1 plus theta 2, the tangent of the sum of two angles. What is the formula? It is given by tan theta 1 plus tan theta 2 divided by 1 minus tan theta 1 tan theta 2. So apply this formula repeatedly to this equation by taking tangent, apply this formula repeatedly, you will get a polynomial equation in omega after simplification. And then you can find the roots of that polynomial equation either by trial and error or by using some computer program. In general, to find out the root of a polynomial, there is no alternative but to use a computer program or to use a method of approximation like Newton-Raphson method or Horner's method, and there are so many of them, to get an approximation for the root. So this is the second method for determining imaginary axis intersections, or to find out whether the root locus branches intersect the j omega axis at all for a non-negative value of k or for a positive value of ka, and then once you know that point where it intersects, finding the gain ka is very simple. On the calculator, it simply involves calculating distances and taking the product of distances to the poles and dividing it by the product of distances to the zeros. So this is the second method, but as I said, I would not recommend it to you because it involves lots of calculations and mostly trial and error kind of thing. Fortunately for us, we have this third method which is based on a result which was discovered and proved by Routh more than 100 years ago. And this involves the construction of a table, or sometimes it is called an array of numbers, and the array is called a Routh array or a Routh table. And then it can be used also to provide or to enable us to deduce a condition of stability which is sometimes known as the Routh criterion or the Routh test. The method of constructing the array or the table may be called the Routh algorithm. I hope you have come across the word algorithm already in your computer science courses. Any regular procedure, step-by-step procedure for solving a problem is called an algorithm for a problem. Now the Routh table or array procedure is a procedure which enables you to find out whether a given polynomial has any roots in the strict right half plane, that is, whether it has any roots with a real part which is strictly positive. Now I will illustrate the Routh array by taking a few examples, but first a few simple things. It is not too difficult to show that if you have a polynomial of some degree in which one of the coefficients of degree, of course less than the degree of the polynomial, is 0, or as we may say the corresponding power of s is missing, then this polynomial will be such that it will not have all its roots in the left half plane. It may have a root on the imaginary axis, or it may have a root in the right half plane. So it is going to be a bad polynomial from the point of view of our stability criteria condition. It is going to be a bad polynomial, and that value of Ka, the gain Ka, is going to be a bad choice of the gain. For example, here is a simple polynomial s cube plus 6s square plus 5. What is the degree of this polynomial? 3, because the highest power of s is of degree 3, s cube. Now this is a polynomial in which one of the coefficients is missing, or it's the coefficient of that power of s is 0. Which power? The first power. I can of course rewrite this as s cube plus 6s square plus 0 into s, or s raised to 1 if you wish, plus 5 into, I will write even s raised to 0. So here are the powers, s to the third power, second power, first power and 0th power. One of the coefficients is 0. So this polynomial is bad. That is, its roots will be such that not all of them will lie strictly in the left half plane. Now for this you do not have to try to factorize it at all. This is surprising, but this can be proved that if a coefficient is missing, then that polynomial cannot have all of its roots in the left half plane. At least one root will be either on the j omega axis or in the right half plane. Another simple result. Here I have a polynomial s cube plus 6a square minus 4s plus 5. Now here the power of s is not missing, but one of the coefficients is negative while all the other coefficients are positive. Well, then such a polynomial is also bad. What about the polynomial minus s cube minus 6s square minus 4s minus 5? All of its coefficients are negative. Well, I cannot conclude that it is bad. So the rule is, if in the coefficients of the polynomial there is a change of sign anywhere, then that polynomial is bad. If a coefficient is missing, then that polynomial is bad. So sometimes you can tell a bad polynomial by what may be called inspection. Inspection meaning just check whether a power of s is missing or whether there is a change of sign as you go down the coefficients of the polynomial. Alright, so I have the polynomial s cube plus 6s square plus 4s plus 5. No power of s is missing, all the coefficients are positive. So what can I say right now? Nothing. I will have to invoke or use some further rules, and the Routh array or table will enable us to answer this question. But what about the polynomial minus s cube minus 6s square minus 4s minus 5? Well, it is just nothing but the negative of, and therefore minus 1 into s cube plus 6s square plus 4s plus 5. So the roots of this polynomial and the roots of this polynomial are going to be exactly the same. So all the coefficients negative is not necessarily bad. You do not have to have all the coefficients positive. Of course, one can always change the sign of all the coefficients throughout by saying that I am multiplying the polynomial by minus 1. That does not change its roots. So if you do not want to see negative numbers, if they are all negative, you can make them all positive, no problem. But there must not be any change of sign. Now if there was some coefficient which was positive and some coefficient which was negative, if I multiply by minus 1, then obviously the plus will become minus and the minus will become plus. So there will be some coefficient which is plus and some coefficient which is minus. So the polynomial is bad. Let me look at another polynomial, which is 2s cube plus 12s square plus 8s plus 10. This polynomial is different from the first polynomial. But are they really terribly different? No, because the second polynomial can be written as 2 times the first polynomial. Now again, it does not require too much thinking to see that the roots of the first polynomial and this polynomial are exactly the same, because wherever this is 0, the other one is 2 times 0 and therefore 0. Wherever this one is 0, so 2 times something is 0, so that something must be 0 and therefore this polynomial is 0. So what is the upshot of this? The upshot of this is that whenever you have a polynomial and you are going to look at, or you want to study where the roots of this polynomial may be using some of these tests, you can look at the highest degree coefficient and change it to 1. that is multiply the polynomial by a number, either a positive number or a negative number, to make the coefficient of the highest power 1. The coefficient of the highest power is called the leading coefficient, and so I can always change the polynomial into a polynomial whose leading coefficient is equal to 1, and therefore I don't even write it. I don't write 1 into s cube, I simply write s cube. It's convenient to do this because then at least one of the coefficients is a standard coefficient, namely 1. Such a polynomial is also called a monic polynomial. It's not necessary that your polynomial should be a monic polynomial, but it's useful to make it monic because of a reason that you will see, and it's very easy to make it monic. All you have to do is multiply it by a suitable number. All right. So let me look at the polynomial once again. S cube plus 6s square plus 4s plus 5. Now some of you may try to guess the factors of this polynomial, but they are not going to be easy to guess. There are some simple rules. For example, there is what is called the remainder theorem. If you use the remainder theorem, you can find out whether a particular number is or is not a root of the polynomial. But in fact, you don't have to use the remainder theorem. All you have to do is replace s by any number and check whether this thing comes out to be 0. You can see that if I replace s by plus 1, that's not going to be 0. So 1 is not a root of this polynomial. In fact, any positive real number will not be a root of this polynomial because all of this will add up to a positive number. But there could be roots which are negative real numbers, or there could be roots which are complex. It's not easy to figure out at all from this polynomial what its roots may be. Of course, this is a very special polynomial. It is what is called a cubic, and there is even a formula for the roots of a cubic. But I would advise you not to use that formula. For one thing, the formula is fairly difficult to remember, and secondly, the formula may require the use of complex arithmetic. It is better to avoid that as far as possible. Fortunately, the Routh table method gives us a method of answering this question. It does not tell you what the roots of the polynomial will be, but it can tell you where the roots of the polynomial may or may not be. I will explain as I go along. Now, the first step in the application of the Routh algorithm: take the polynomial, then the books will of course tell you do this, but let me tell you what is it that you are doing, and then maybe if you spend a little time you can understand why one is doing that. Now this polynomial, highest degree term is s cube. S cube is an odd power of s. It is the third power of s. It's an odd power. Is there any other odd power of s in the polynomial? Yes, 4s. 4s is a term which has an odd power of s. So think of these two together, s cube plus 4s. S cube is an odd power, s or s to the 1 is an odd power. Of course, they are multiplied by some coefficients, 1 here, 4 here. So this part that we have taken out from the whole polynomial is called the odd part of the given polynomial. Now what remains? What remains is the term 6s squared. Now what is the power of s here? 2. 2 is an even number. The other term that remains is 5, but I can write it as 5 into s raised to 0. By the law of indices, s raised to 0 is 1, and we treat 0 as an even number. And of course, you should be able to answer why 0 is treated as an even number and not as an odd number. Now if you take these two terms together, then this is said to be the even part of the polynomial. So given the polynomial, think of splitting it into its two parts, the odd part and the even part. The odd part is here, s cube plus 4s. The even part is here, 6s squared plus 5. The odd part has the highest power 3, s to the 3. So the degree of the odd part in this case is 3. What about the even part? The even part highest power is s to the 2. So the degree of the even part is 2. So in this case, the degree of the odd part is greater than the degree of the even part. Now, from the polynomial, how do you pick out the odd part? Because in the procedure, once you have understood, it is not necessary to write down the two parts separately. So, I start with the highest power, that is odd, that is s cube. Then I leave one term which is 1 degree less, go to the next term or the next odd power of s, this is s to the 1. So, I will get 1 s cube plus 4s, that will be the odd part. What will be the even part? Start with the highest even power, that is this 6s squared. So, 6s square, skip one term and go to the next lower even power of s, in this case s to the 0. So, I will get 6s square plus 5 into s to the 0, and in this case, because the degree of the polynomial is an odd number 3, the odd part is of degree 3, the even part is of degree 2, and therefore, the degree of the odd part is greater than the degree of the even part. Now, I can take an example in which the situation will be reversed, and so let us take a look at that example. So, here is a polynomial which we will make use of later on. I have s to the 4 plus 3s cube plus 6s squared plus 12s plus 8. What is the degree of this polynomial? The degree of this polynomial is 4, because the highest power of s is s to the 4. Is it monic? Yes, because its coefficient is 1. Now, what is its even part and what is its odd part? Well, start with the highest power, which is even, s to the 4. The next lower even power is 6s square. The next lower even power is 8. So, the even part will be s4 plus 6s square plus 8. What about the odd part? Start with the highest odd power, it is 3s cube, and the next lower odd power, that is 12s. So, the odd part is 3s cube plus 12s. So, in the Routh test or Routh array or table construction, what we are going to do is we are going to split the polynomial into its odd and even part. That is the first step, but we are going to do it in such a way that we will start constructing the table with this odd part and the even part. So, for the polynomial that I started with, namely s cube plus 6s square plus 4s plus 5, starting with the highest power, I will get s cube plus 4s, and so I will start writing my table or array in this fashion. Since the highest power is s cube, I am going to write here s cube on the left hand side, and then I am going to put two dots here. This is the English punctuation symbol read as colon. Instead of that, of course, you can draw a vertical line if you wish. So, I am going to write here s cube colon, and what I am going to write are not the two terms s cube and 4s. So, the polynomial is actually s cube for 4s, but what I am going to write is simply s cube, the coefficient of the s cube power, which is 1, and the coefficient of the next lower odd power, which is 4. So, this is the first row of my table that I am going to write, s cube here, 1 and 4. Now, the textbook may tell you do it this way, but if you do it this way without understanding what you are doing, then it is not really worth learning the whole thing. What you are doing is, from the polynomial, you have separated out its odd part, and this is just a compact way of writing the odd part. The s3 tells you that this 1 is multiplied by s3, and the next number 4 tells you that 4 multiplies the next lower odd power of s, namely s to the 1. So, s cube 1 and 4, from that I can conclude that the odd part is 1 into s cube plus 4 into s. Now, the next row will be the even part. The even part, therefore, I will write down s squared here and then write down the coefficients. The coefficient of s squared is 6, so I will write down that coefficient here, and the next lower even power of s, the coefficient is 5, so I will write down 5 here. So, this is the way to start off the table, and the first two rows of the table are written like this. In other words, the first two rows of the table give you, in a compact way, the odd part and the even part of the original polynomial. Of course, here the odd part was of higher degree, so I wrote it first. The even part was of lower degree, so I wrote it next. For the other example that we are looking at, it will be just the reverse. So, if the polynomial is s to the 4 plus 3s cube plus 6s square plus 12s plus 8. Then how do I begin? The highest power is s to the 4. So, I will write down s to the 4 here, colon, the coefficients of the even powers. S to the 4, 1, it is also monic. Next one is 6 and next one is 8. So, these are the 3 coefficients in the even part of the polynomial. The even part is 1 into s to the 4 plus 6 s squared plus 8. Below that, I will write down the odd part of the polynomial. The odd part starts with 3s cube. So, I have written s cube here. I will write the coefficient of s cube 3. The next lower power, odd power of s is s to the 1. The coefficient is 12. And what should I write here? Well, nothing, because there is no further power of s. So, it is better to put a cross or a dash. There is no entry to be filled here. Do not write a 0. There is no power of s here. There is no s to the minus 1 because we have a polynomial. We do not talk about s to the minus 1. So, do not write a 0 here. Either put a cross or put a dash. But do not forget to put a cross or a dash, because then you know that you are not forgotten to write something. There is no entry here. The polynomial, therefore, I can read now is, looking at this s to the 4, 1 into s to the 4 plus 3s cube plus 6s square plus 12s plus 8. Or if I go back to the earlier example, s cube is the power here. So, 1 into s cube plus 6s square plus 4s plus 5. So, in this case, the odd part appears first, followed by the even part, because the whole polynomial is of odd degree. In this case, the even part appears first and then the odd part, because the polynomial is of even degree. You do not have to remember this. If you understand what is going on, you do not have to really remember a rule that if it is odd, do this, if it is even, do this. Look at the polynomial. It requires very little practice to see the odd part, that is the odd powers of s, and the even part, that is the even powers of s, and start writing them down. The only thing is, the higher degree polynomial should appear first, because that is the way I am going to tell you the rule. Okay? So, the first step in the construction of the Routh array or the table is to write down these two arrays correctly. Let us take an example that I mentioned earlier, in which one of the coefficients was equal to 0. What happens in that case? Of course, I told you that it is a bad polynomial, and Routh rule tells you also something about it. In that case, the polynomial was s cube plus 6s square plus 5. So, let me split it into its odd part and even part. Degree is odd, so I will start with s cube. What are the powers of s cube? S cube is 1. What are the powers of s, odd powers? S cube has coefficient 1, s to the 1. Now, I can't put a cross or a dash here, I have to put 0. The coefficient of s to the 1 is 0. So, s cube is 1, s to the 1 is 0. What about the even part? S squared is 6, and the constant term, or s to the 0 power, is 5. So, these will be the first two rows for this polynomial. And if the polynomial has a negative coefficient, you can still write down the Routh table. But as I told you, the polynomial can be immediately concluded to be bad. But how bad? If you want to find that out using the Routh algorithm, then you should work out the Routh table. So, I have s cube plus 6s square minus 4s plus 5. So, where do I start? Start with s cube. So, s cube coefficient is 1, s to the 1 coefficient is minus 4. Next, the even powers, starting with s square coefficient is 6, constant term is 5. So, this is how I start my table. The first two rows of the table therefore correspond to the odd and even part of the given polynomial. So, we are splitting the polynomial into its odd part and its even part, and we start the table by putting down these two polynomials in a compact form like this. Now, the next step is a little involved, but with practice one can get used to it without any difficulty. Now, the next step involves something like the following, and I will illustrate it not by taking actual numbers, but by showing two rows. Let us say I have some power of s, let us say it is 10. So, I have some coefficients here. So, I am going to put down x, meaning that there are some numbers, not all equal necessarily, s to the 10, s to the 8, 6, 4, 2 and 0. So, whatever they are. The next power of lower power is the odd power s to the 9, and there will be some numbers. Once again I am going to put x, x, x. That does not mean they are all equal. There are some unknown entries at the moment. Now from these two rows I am going to construct a new row. I am going to give it a row heading which is the next lower power of s. So 10 here, 9 here. So I am going to label it s to the 8, and I am going to write down the entries of this row by following a particular rule. But before I tell you what the rule is, if these two are really polynomials, this is an even polynomial and this is an odd polynomial, and if I write a new row and this new row the heading is s to the 8, then what would this row mean, or what would it stand for? It would stand for an even polynomial of degree at most 8, an even polynomial of degree 8. So in other words, from the even polynomial of degree 10 and even polynomial of degree 9, by following a certain rule I am going to obtain an even polynomial of degree 8. And of course the procedure does not stop here. From these two rows I obtain the next one. Then what I do is, from the two rows that I have, the last two rows that I have, I calculate the next one. So from that I will calculate s to the 7 row, and I will keep on doing it. We will take a numerical example to illustrate this, but first from these two rows how do I obtain the next row? So the basic idea of the Routh array is, from two appropriate rows generate the next row. From two rows whose coefficients are given, calculate the next row. Now what is the rule for calculating the coefficients? As I told you, the first time you see it, it may appear to be very difficult, but with practice you can get used to it and you can apply it without difficulty. Now there are these two rows and I want to find out the next row. First of all, in the second row, the first entry that occurs here is going to play a different role in what we are going to do. So this element we will call the pivot element. So think of this as a very crucial element. Think of it as a pivot element. A pivotal person is somebody who is very important in an organization. So this element plays a very important role. So think of it as the pivot element. Now what you do the following, and you can see that when you write the table properly, the rule can be understood without any difficulty. From the pivot element, go like this, easier shown than said, that is, go to the upper row but go in the towards the right. So it is this element across it this way. Take the product of these two entries. So the way I like to remember it is the pivot element into or multiplied by this element. Take that product. From that product subtract this product, the product of these two elements which are located crosswise like this. So this product minus this product, calculate that difference and divide it by the pivot element. That will be the next element, first element in the next row. So this element in the next row will be, take the pivot, multiply it this way, take that product, from that subtract this product and divide by this pivot element itself. That is the first entry in the next row. What about the second entry in the next row? For the second entry, do a similar thing, start with the pivot element, but now go up, but go one step further to the right. So this number into this number, minus what? Minus again one step further to the right into this number. So this into this minus this into this divided by that gives me the next entry of the third row or the next row. Now keep on doing this till you run out of such products to form. So let us take an example and illustrate. So let me take the example s cube plus 6s square plus 4s plus 5. So here is the first row, s cube 1 4 s square 6 5. There are no further entries, so I am not even writing dash or cross. Now the next row, the heading is going to be s to the 1, and I want to find out the entries. So this is my pivot element. So 6 times 4, how much is that? 24, minus 5 times 1, that is minus 5. So the difference is 19. divide that by the pivot element. What is the pivot element? 6. So, the number here is 19 by 6. That is the first entry here. Now, what will be the second entry? Well, none, because there is no entry here. To go crosswise, there is nothing. Don't think of it as 0, there is nothing. Similarly, there is nothing here. So, there is no more calculation to be done and I am finished. And that is right, because s to the 1 row, what is the polynomial? It is a polynomial whose highest power is s to the 1, and is there an odd polynomial? Is there going to be any other term? No, because s is the smallest odd power of s that you can think of. So, that is it. If you want, I can put a dash here that there is no number to be filled in here, alright. So, my next row calculations are over, but my table calculations are not over because I have the power s to the 1. So, I will go one step further, s to the 0, and how many coefficients will it have? Only one coefficient, because the polynomial of degree 0 is just one constant. So, I have to find out this number here. Same rule now, but now instead of the first two rows, I am now to look at the last two rows that I have obtained, this one and this one. Now, what is my pivot element? It is not 6 anymore, it is this. This is my pivot element, right. So, the same rule now, this pivot element into this number minus this number into this number, but there is no number here. So, minus nothing. So, in other words, I have 19 by 6 into 5, that is the product. From that, nothing is to be subtracted, divided by 19 by 6. So, what is the number here? That number is just 5. From the even polynomial corresponding to this row and the odd polynomial corresponding to this row, I have obtained an even polynomial corresponding to this row. And now I have reached the end of the table because the power is s to the 0 constant. There is nothing less than that. The lowest degree in a polynomial is the 0th degree term or the constant term. So, my table ends here. So, it is as simple as this. Of course, the degree of the polynomial was 3, therefore, the work was not really very much involved. But what if the degree is higher? Then I will have to carry out my calculations for a larger number of steps. At this point, let me just tell you very quickly what the Routh criterion is. That is, after these calculations have been made, Routh's theorem tells you a very powerful result about this polynomial. Have I factorized the polynomial? No, I have not even guessed the factors. Is s plus 1 a factor? I do not know. S plus 2, I do not know. Have I found out any root of the polynomial? No, I have not factorized the polynomial. I have not found out any root of the polynomial. I have not used my pocket calculator for that purpose at all. I have not used any computer program. All I have done is written coefficients of the polynomial and found out some new numbers by using this cross multiply, subtract and divide kind of arrangement, and I kept on getting numbers till I filled up the table like this. Now, Routh tells you that what you should do is look at the first column of this table. The first column of this table has entries starting from the top 1, 6, 19 by 6 and 5. They are all positive. More generally, they could be all negative. But if they all have the same sign, and that means they are all positive, no number is 0, or they are all negative, no number is 0 in the first column, then this polynomial will have all the roots strictly in the left half plane. That is, if the root is real, it will be negative. If the root is complex, it will have a negative real part, and there cannot be a purely imaginary root of this polynomial, s cube plus 6s square plus 4s plus 5. So, really how wonderful is it, without factorizing the polynomial, without trying to find out any root by trial and error, by computing the table in a particular way and by looking at entries in a column of that table and merely by looking at their signs, are they all positive or are they all negative, we are able to say something about the location of the roots of that polynomial, namely all the roots of this polynomial are strictly in the left half plane, and therefore, this polynomial is a good polynomial. Now, this is really a result which the first time you look at it looks unbelievable, that without finding the roots of a polynomial you are able to say something about the roots of the polynomial.